Stanford University.
Okay, I want to hear a little bit more about your recruitment to Stanford. You mentioned that there was an earlier offer, and then in the late 60s. How did this come about?
Well, I mentioned that I was a little bit unhappy with the dean. Nice fellow, but he was devoting too much time to Washington and not enough to Cambridge, I thought. And then, of course, the protests began against the Vietnam War, and engineering was like a target. They would come and protest, and they'd even one house invited me to come, and then they proceeded to bombard me with questions about why I was building helicopters in Vietnam, which I wasn't doing, of course, but they thought I was. So that was it began to be very unpleasant in the protests, and I had these thoughts about going back to the West that I mentioned before, which I loved, and so the two combined, when I got an offer from Stanford, a second offer, they gave me one that I mentioned, and then they had a new dean, and he came in and he offered me a job. And the job was to come in to the Applied Mechanics Department, which existed then. It's now a division of mechanical engineering. But I replaced, quote unquote, Rudy Kallman, who was teaching in the applied mechanics, and he had made a wonderful invention called the Kallman filter, which we will talk about later. But anyway, he left to go back to ETH in Switzerland and Florida, University of Florida, half-time. Anyway, so there was a vacancy there, and they thought of me to come there because there was a lady professor named Irmgard Flugelotz, was a wonderful lady, who did both fluid mechanics and optimization. And bang bang control was one of her specialties. She wrote a book on it, marvelous book. And so I kid that it took two professors to replace that one woman professor, Irmgard. John Spreiter came on board at the same time. He was the aerodynamicist and I was the controls guy. So we covered both of her specialties.
So she was getting ready to retire?
She was getting ready. She hadn't retired yet, but she was getting ready. And I picked up a couple of her students. I guess she did retire because I came and these two wonderful students were dropped right in my lap who had worked with her and wanted to continue on doing what in the field that she was working in. So.
And did you ever get to meet her?
Oh yeah, she stayed on and she passed away about 10 years after that. She had very severe arthritis in her hands, but she was a sweet lady, and she had a wonderful history. She had worked with a great German aerodynamicist, and what's his name? I forget it at the moment. But she had been one of the few, in fact, the only woman graduate student of his. And I tell a great story about that. She and Walter Vincente in our department got to know each other very well. And she told him that she remembers going to tea after the seminars in Göttingen, and the lady who fixed the tea would not fix tea for her because she shouldn't have been there.
Oh my.
She was a woman.
I see.
So she'd fix her own tea. Interesting little story. And Prandtl was his name. Prandtl was the professor's name. The most famous German aerodynamicist. Did so many wonderful things. But so now where was I again?
So I just want to stick with her for a minute. So were you familiar with her work then? It sounds like it was
Yes,
really
I
very
was.
much in your area.
And she'd written this wonderful book I call it bang bang control. She called it contactor control, which is the same thing. You turn the control on or off. There's no in between. It's either on or it's off, and or plus. Maybe it's minus, plus, 0, and plus. And it's much more difficult, well, it was at that time, to design a control that operates that way. Whereas it was simpler to design it. That's just all you needed was a relay. And so she wrote this wonderful book on relay control. And then I picked up these 2 graduate students of hers. And one of them, again, was a German fellow on a NASA fellowship for the Marshall Plan. And he, what's his name now? I have one of these senior moments. He was a wonderful guy, and he worked on a problem which I generated, which was to use the Kalman filter to design the control of a spacecraft to align the gyros using a horizon sensor and a rate gyro. And we later got a prize for that one. He did a wonderful thesis. And it was Willie.
Right.
Okay. I forget
We'll remember in a minute.
I forget his last name. But Willie went back to Germany and worked for the German NASA in Munich, which is, and he invited me and Helen to come there. I gave some lectures and we spent some time with him in Germany there. Munich and that area is just beautiful. And they lived in a suburb near the laboratory with a big lake nearby. What was his name? the Ammersee. And it's right near Oberammergau, which is quite famous for 10-year pageants. And so we had a wonderful time hiking and visiting around Germany there. His wife she had a strikingly German name, and they named her. They had a child while they were here as a graduate student, named him Wolfgang. And I had a niece who came to Stanford, and so we invited her up to a house now and then, and she came and met my German student and asked about the name of the baby. And I said, Wolfgang. He said, what? Wolfgang? There's apparently a list of acceptable names in the Catholic Church in Germany, and Wolfgang's one of them, you know.
Interesting.
And her name, which I wish I could remember, was another one that was quite unusual. But anyway, just a very nice German family. So I knew these 2 German students who were benefited from the Marshall Plan after World War II.
Yes.
Who were so nice.
Yeah.
I began to get an international attitude. The good people are everywhere.
Right.
And I had Indian students, I had Japanese students, all wonderful.
Right.
Just great.
So you came to Stanford and you're in the applied mechanics, and I thought it was very interesting that shortly after you get here, they convince you to be the chair of the department. So can you tell me how that worked? I found that surprising that the new guy comes in and
I found it
put him in
surprising
charge.
too, and
Yeah.
I'm sure the older professors in applied mechanics found it kind of surprising. But this was Dean Pettit, and I think he was interested in trying to bring a more modern flavor to applied mechanics, and thought I might be one to promote that. So I took that job on for 2 years, and Professor Kane was also one of the younger professors in applied mechanics, and he worked on dynamics of complicated systems, spacecraft, spinning spacecraft, and so forth. So we got along, and but after 2 years, it was time for Nicholas Hoff to retire as head of the Aeronautics and Astronautics department. And so Pettit asked me if I would take that one, and I thought that's really what I was interested in.
Right.
And so I did. And again, jumped from the frying pan into the fire with all kinds of problems in the aero department. It was a new department. It had been started in 1957. Here was 68. So it had been 9 years, and it had accumulated assistant professors who were up for promotion. There's a rule that after 7 years you have to go up or out.
Right.
And so I was faced with 4 of these assistant professors who were at that stage. And so that was not a very pleasant job, because I had to get rid of all 4 of them.
Oh my.
The research they were doing was not up to what was expected. And one of them had some other problems, which I won't mention. But so I got as I say, I went from frying pan into the fire. I had this 4 professors to deal with. But then, of course, I was responsible for hiring new assistant professors to take their places, which was fun. So I hired a few good ones, I think.
So how did you evaluate whether or not somebody's research was kind of, what was the procedure then for determining that?
You get a list of publications, and you also get reports on how he's teaching. It was formalized later on that the Tau Beta Pi, the honorary fraternity engineering, started giving out questionnaires to students, graduate students, and asking about the quality of the teaching. And we could get copies of those. So I think that was an important step, because we wanted professors who could both do research and were good teachers. And sometimes they don't go together.
Right.
And that's one of the reasons we had. And evaluating the research is done now by writing to, and even then to people in the field whom we know and other universities whom we think might know of his work, and ask their opinion. And so these 3 guys didn't stack up on the research. 2 of them were pretty good teachers. No, 3 of them were good teachers, but they didn't have the research. And so that was a painful part of being a department head, is that you had to let people go.
Yeah.
And but we got some new people in, and went on from there.
And how did that part work, the recruitment process? did you sort of have an idea of what type of a researcher you were looking for?
Yeah, we had mainly just the field, but if we had an applicant who was not in one of those fields but was doing outstanding research in the field, we'd take him. And I think that's still the attitude. It's the quality rather than what they're working on,
right,
that you look at. And but that's a complicated procedure. You get a department committee who looks at it and form a special committee for each appointment, and they look at all the candidates and bring it to the department, and the department decides, and then we send it to the dean, and he says yes or no, or then it goes on to the provost, and he says yes or no.
Right.
So there's a lot of hurdles to get through in appointing somebody.
So when you took that job as the chair of the department, did you have kind of a vision of what you hoped to achieve, or?
I just hoped I could be as good as Nick Hoff was, the guy I was replacing. He was outstanding as a teacher, researcher, and administrator, and a very nice man.
Yeah. What was his personality like?
His personality was wide open, friendly. He just got along with everybody, and he was Jewish, and he had come to Stanford to get a PhD with our famous Russian professor
Timoshenko.
Yeah, I can't think of his name at the moment, but he got his PhD with him, and so he had a leaning towards Stanford. He went back and he taught at Brooklyn Polytech for many years and became quite well known for head of the department back there. So Dean Pettit invited him to come out here and start a new department of aeronautics. Aeronautics had up to that time been a subtopic of mechanical engineering, a sub-department. But Durand had really started aeronautics in ME back in post-World War I.
Right.
Yeah. So where was I now?
So we're talking about Nick Hoff and what
Nick
his
Hoff.
background was.
Nick Hoff was very good at dealing with people, and I had another professor who wasn't doing very well either. After I got rid of, this was a professor with tenure that I wasn't doing very well, and so you have one handle on a professor like that, is that not to raise his salary. So I didn't raise his salary for many years. And again, I knew that he was not going to like that very much, but he had bad reports on his teaching, and his research was not so good. But fortunately, he got an offer from Taiwan to go to a university in Taiwan to be head of the Department of Aeronautics there. And he went there, and he was a great success.
Oh, interesting.
So solved two problems and helped him, and
right.
Lucky to help him too. And but so I fired 5 professors that Nick Hoff had hired in the process over a period of years. Fired is too strong a term. I didn't promote them.
Right.
Yeah.
And was the department able to remain cohesive after that kind of a disruption?
Yeah, it was. There was really no problem with that. Yeah.
And what kind of a sort of atmosphere did you sense or hope to cultivate there? I mean, was it a place where everybody kind of did their own thing, or how would you describe it?
We'd have department meetings, maybe once a quarter or something, and I was always open to new suggestions, and I got some good ones. You don't you don't supervise professors, they do their thing. And you simply look at their accomplishments. You don't tell them what to do. So it's like herding cats to be a department head. And so I maintained a research program. At one point, I had 10 PhD students, and also being department head, which was quite a load.
Yes.
And but it was fun. I had these 10 marvelous students to work with, and
Yes.
so they said, and I would have weekly meetings with them, and I'd ask each one to recount progress or something interesting that had happened to him during the week. So we developed a friendly cohesiveness in the research group, which I think worked out very well. I had on my 90th birthday last October, I had my PhD students from Harvard and Stanford gave me a 90th birthday party. And I had even 2 of my Israeli students come all the way from Israel.
No kidding.
And so the 2 guys who really promoted the birthday party were 2 of my Harvard students, Jason Spire and names. I can't think of his name. Just terrible. He's such a nice guy. Well, anyway, that was an indication that maybe I'd done something right with the 65 PhDs. It was very heartwarming.
Yes, that's
And
incredible.
so that took place before my family 90th birthday,
Oh, boy.
which was on the real date.
A lot to celebrate. So,
But I've kept in touch with almost all of those students, and it's been a great pleasure. Visited many of them in the countries where they came from, and in South Africa in particular.
you have a whole network out there.
What?
You have a whole network out there
Yeah.
of Bryson.
I had 2 students from South Africa, and now one of them is vice rector, which is like provost of Stellenbosch University, which is outside of Cape Town. It's interesting. That university bears a relationship to Cape Town like Stanford does to San Francisco.
Oh, interesting.
There's a wine valley just beyond it called Franschhoek, where we have the Napa, and the wines in both places are very good. And right behind the university there is a range of mountains, so it looks like the peninsula here with the mountains. So
Reminds you of home. Interesting.
I asked my 2 South African students how they compared South Africa with the Bay Area. They said, "Well, we like the South African a little bit better."
Oh, interesting. Yeah.
Which is unusual. People come here and they say this is the best place in the world to live.
Yeah, it's been a part of Stanford's criteria for success, I think.
Yeah.
So let me just ask you a little bit more about the department leadership role.
Okay.
So did you have to deal a lot with the sort of senior administration, the deans of engineering and the...
Yeah, we had a weekly meeting of the department heads with the dean, and he would give us news about what's going on in the engineering area, and also take up the promotions that had been the nominations would come up for approval by the department heads. I started out with Dean Pettit and ended up with Bill Kays. And so that was interesting. At one point, I was an alternate for the provost's, what do they call it? The committee that looks at it at the provost level. And so I attended a couple of meetings there. very much impressed with the administration.
Yeah. Was there a sense of what the engineering school was trying to achieve in the 1970s? Was there any major initiatives or anything that you felt you were a part of?
Well, of course, electrical engineering is the big thing at Stanford, always has been, and so the deans had come from there. I think Bill Case was the first mechanical engineer to be dean, and then we reverted back to electrical engineers.
That's right.
But no, they were starting up Silicon Valley, really, and so that was just tremendous. We were in aeronautics. We were next to Lockheed and NASA Ames, which was one of the big research facilities in aeronautics. Lockheed had a big research department. I interacted with them, and I interacted with the head of the NASA Ames Research Center. So we worked out a deal for a lot of the people to come from both Lockheed and NASA Ames to get master's and PhD programs part-time.
Right.
Those are the only part-time students that were allowed, were those that were in this honors program. And that was really a very good thing for us, and I think for them.
So this is the Honors Co-op program.
Honors Co-op, yeah.
And they would come and learn basic aeronautics principles, or?
Yeah, but took same courses that we gave to everybody. And Walter Vincente, who you know, was recruited by the famous dean who was also provost. What's his name? Terman. Gosh, how could I forget that? He was recruited by Terman because Terman had heard him give a lecture on his work at NASA Ames and knew that he had gotten his graduate degree here. So in those days, Terman didn't even have a committee. He just says, "Okay, you're hired." Offered him a job right on the spot to come. And nowadays you have to go through multiple committees and reviews. But that's the way he built it. He's famous for saying he wanted steeples of excellence.
That's right.
That was his, and he sure did.
Yeah. He
did. And I think he was behind my hiring too, although I think Pettit was also involved.
Right. Did you have to worry a lot about funding as the chair of the department?
No, I didn't. Well, I did in a way, but the individual professors were responsible for writing their proposals. I didn't even review them. Maybe I should have, but I didn't. I can't be expert in all those fields, so I wasn't sure. So they found their own support from outside, mostly from NASA, but also from AFOSR and Naval Research Operation. Very few from industry, some.
Yeah.
And of course, we'd get students from Boeing who they would send and pay their way here through the PhD. I had a couple of those, and then the foreign countries, I had students from Japan and Singapore and South Africa, all who paid their way. So
they went through the regular application process to the department.
Yeah, but then they'd come and you could do a research project with them with out any extra funding. I had this one marvelous guy from South Africa, Arnold Schoenwinkel, who, as I told you, is now the vice rector at Stellenbosch, and he wanted to do experimental thesis. Well, that you have to have equipment and so forth. So my colleague Bob Cannon had started this aerospace robotics laboratory. He followed me as chair of the department, and so he kindly let Arnold use his lab and used his technicians to build equipment. So Arnold came, and his PhD thesis was fun. He built a robotic unicycle, and his thesis defense was on a tennis court where he had the radio controls and was directing it around on the tennis court. And the way of keeping it up, as it falls forward, you speed up the motor to go under it, keep it up. The one for falling right and left is a bit more complicated. And for that you need some gyros or some attitude sensors, and they were too expensive. So what he did was to find another way to do it, was to put little trailers on the axle of the unicycle wheel, which trailed down to little wheels on the ground. And so as the unicycle tilted over, you could detect by the difference these two things went down, developed an angle. And so it's a bit of a fake, but not so bad. And so with a unicycle and a bicycle, you turn into the direction you are falling, which is quite
counterintuitive.
It's surprising. Most people don't even know that.
Right.
But they'll learn it if they get on the edge of a sidewalk and they're right on the curb and they want to turn back in. You can't do it. Because you first have to turn a little bit off the curb in order to get the wheel to turn. Oh. So that was an interesting PhD thesis. He went back, as I told you, to South Africa, and he soon in 5 years he was the head of the EE department, and in 8 years he was the dean of engineering.
Wow.
In 5 more years, and he was the vice rector.
Yeah.
So he's an outstanding guy.
While we're talking about PhD students, and you had 65 PhD students, did you have a particular approach to working with them?
I think the main one's just being friendly and helpful. Most of them, most of the time I'd provide the problems. I'd give them several problems I thought might be interesting. They'd pick one. But a few of them came with ideas like Arnold of what he wanted to do. And so I had enough of them that I could have a weekly research session, and I think where we each talked about the research, they helped each other. And that seemed to work pretty well.
Right.
And got all of them to be friends with each other. And
was there cross-pollination between departments at that time, or was people doing aero-astro pretty much their own cohort?
We had one big program with physics, which was the what's it called?
The gravity bee?
The checking Newton's general theory of relativity. I forget what
Was it the gravity bee?
Gravity probe B,
yeah.
Thank you. Gravity probe B. And that was Bob Cannon, and Bob Cannon was in on the beginnings of that. He made the suggestion to the physicists that space was a place without any, he could put something spinning up there that would spin for a long time, no air to slow it down. And and then Dan DeBray picked up on that, and then Bob Cannon hired Brad Parkinson, who came and managed that project, and also became a professor and had students on GPS and so forth. So one thing leads to another, as Cannon likes to say.
Yes.
And so in the physics department, it was Bill Fairbanks, I think it was a fellow who did low temperature helium, which was an essential part of the Gravity Probe B program, to have a very cold detector. And that's was a remarkable problem. It involved precision engineering to levels that were just way beyond what people thought were possible. At MIT, they'd built inertial navigation systems that were so sensitive they could use them in airplanes for guidance. But that wasn't good enough for the Gravity Probe B. It had to be about 5 or 6 orders of magnitude more accurate. And that's where Debray came in. Mm. He went over to Livermore and learned about precision machining in the Livermore lab, and built the little balls that were used as gyros, a spinning ball. They're about the size of a ping pong ball, and but they're covered with niobium or something like that. And they spun them up and then tracked them without touching them, which is quite a job. And that's the basis of following an orbit that's what we call drag-free, because if you're really following this little ball in space, mm-hmm. and it's following a gravity. It doesn't know about air. It's not in touch with air, so it follows a pure gravitational orbit. And to do that, though, you've got to have it spinning, and you have to detect how it moves, and that is where the low temperature stuff comes in, and the physics to detect how that thing is spinning inside in the gyro. So it was a wonderful collaboration between the physics department and the aeronautics department. Mostly Dan Debray and Bob Cannon.
Right.
I didn't have much to do with it.
Mm-hmm. And so we've talked a little bit about working with graduate students and the collaboration. When you were in the classroom giving lectures, did you have any, I know you've won teaching awards from Westinghouse, and what was your approach to engineering education?
My main objective was to teach by examples. I think most of us learn by an interesting example more than we do from just a laying out of a theory. So I like to find the simplest possible problem that involves the essential thing I'm trying to teach, and use that as a teaching tool. And it worked out pretty well. I think many students told me that they liked it, to learn that way. And in a way, you're teaching two things. You're teaching some applications at the time, and also some principles.
Right.
And so that was one of my teaching philosophies. I like to give hard problems that were interesting too, the ones that really showed applications. I think sometimes the students complained the problems were much too hard, but better that than too easy.
Right.
Right.
And I know that you were involved in an effort to make some films related to engineering education. Could you talk about that? And then I think it was still when you were at Harvard.
Yes, when I was at Harvard. I had Asher Shapiro was a professor of mechanical engineering at MIT, and I got to know him when I was at Harvard. Very nice fellow. He had the initiative to start a fluid mechanics film series. He got funding from the National Science Foundation, and his objective was to make about 25, 35, I forget, maybe 30 half-hour sound, color movies of fluid mechanics phenomena. And the way he did it was to get a committee of about 5 people who were the leading experts in the world on that subject, and have them recommend someone who would make the picture. And then they, the fellow who was then cited, wrote a script and submitted it to that committee, and they criticized it, made suggestions. So you started right at the top of the people who knew these phenomena. And this is Asher's idea, great idea. And then he hired a really professional group of movie makers called Educational Services Incorporation, ESI, headquarters in Watertown near Boston, to make the films. And he had professional directors. Well, I got involved because he asked me to make a film on waves and fluids, which is over there on the table. I had, of course, had the shock wave, which was a big wave phenomenon, so that was featured in the film. But I built a water tank to show the waves in water, which was about the size of my shock tube, 40 feet long and a foot square. And so what we did was to put a piston at one end and push it like this to start the wave going down the channel, and we had a camera on tracks with one guy pushing and one guy on the platform taking the picture to follow the wave as it went down. And after a little practice, I got pretty good at that. What I didn't take into account first is what happens when the wave reaches the other end. Splash up, cover the floor. We finally put a big tank there to catch it. That is like when I built the shock tube when the wave went, and then it knocked the wall down. Anyway, that was an experience. Well, Asher wanted to go on sabbatical. So he asked me, being nearby at Harvard, if I would take over the job of being the chairman for a year while he was on sabbatical. And I was quite honored to be asked. And I lucked out in having some very interesting films made during my year of substituting for Asher. One of them was G.I. Taylor, probably the most famous British aerodynamicist in history. Fine gentleman. He was 80 years old at that time. I was worried a little bit about overworking him. So we asked him, what kind of hours would you like? Oh, he says, not before 6 o'clock and not after 10 o'clock at night. No problem.
Reasonable, yeah.
Well, anyway, he charmed the film director so much so that the film director asked me, can't we make a film of him about his life, like you're doing with me? And so we did. And I think that's one of the better films. Unfortunately, that's not on, I don't think that's on. Later on, they took all 35 of the films and put them on DVDs. And MIT has them. You can get them on the internet. And their place. But they're really very good. There's still many people use them all over the world.
Oh, so they got a good response.
Yeah,
then.
because you can see the phenomenon of waves and shock tubes and boundary layers and all kinds of things. Fluid mechanics is very visual.
Right.
And so that turned out to be a great project, and I was delighted to be involved in it.
Yeah. And did you ever use those in your teaching?
Oh, sure.
Yeah.
I had another very famous professor make a film while I was substituting for Asher. It was Lighthill, James Lighthill, Sir James Lighthill. He's passed away now, but we asked him to make a film with a colleague whose name I forget, on sounds produced by jets. Just still a interesting and difficult problem. And trying to quiet down a jet engine, the exhaust of a jet engine. Well, he got carried away. He plays the flute very well. So the script came, and it starts off with him playing the flute in the pilot's position in the first supersonic plane, which was British, and so upholding the British standard. And then went on for about 2 hours. The script would have been 2 hours long.
Oh my!
And I had told him half an hour. So here I was in a position of a associate professor at Harvard, telling this Sir James that he's got to shorten it.
Move it along, James.
Yeah, move it along. It's way too long.
Yeah.
Well, he did, and it became one of our best films. But it was interesting. And of course, when the film reached a semi-final stage, we'd get that committee back together again and look at the film, and they would make suggestions for changes and improvements. So it was a great undertaking, and it worked out well.
Oh, interesting. Thinking back on your teaching at Stanford especially, was there a favorite course that you taught?
Oh, I like the optimization course. I got carried away with optimization. Once I learned the calculus variations, I made, and computers were coming along then. You can't do interesting problems in the calculus variations without a computer. Just very simple, sort of too simple problems that are not very interesting from the practical viewpoint. So that was sort of the focus of most of my research, was optimization, optimal control. I got involved in optimal control then, which is a sub part of optimization, and that's where Rudy Kalman, the man I mentioned previously, he had done some very wonderful work in optimal control and optimal estimation. If I give you a gyro history and you have a model of the airplane, you can use that model of the airplane and the measured gyro output to estimate the states of the aircraft, its speed, its attitude, and so forth. And this is one of the great discoveries of the modern era, the Kalman filter. You take the measurement and you compute from the current state of the airplane, velocity, angles, what you thought that was going to be, and you take the difference between the measured and the predicted, and then take that error and multiply it by a gain, and feed it back into the model in order to improve your estimate of the states. And it works like a charm, not only in aeronautics, but in even economics, any place where you have a dynamic model to use and you have measurements to go with it. So I went from optimization of flight paths to optimal control, which used the Kalman filter as one component of the optimization of the control. The optimal control itself I had worked on before, and that also was started by Kalman, where you make a state variable model of it, and then have the input controls, and you design the controls so that you optimize a quadratic performance index and the error squared during the flight. So that's really a calculus variations problem. Subsequently, I made some algorithms for that, which were pretty good, but then along came some people who used the discrete step version of dynamics, and they made some even better programs and mathematical codes. So I adopted that later on in the second version of my book on optimal control, and those algorithms work just like a charm. You start with a model and a guess about the optimal control, and iterate a few times, and boom, you got optimal control. And that was really fun. I was working at Raytheon when I first came across the Kalman filter, and having been at Hughes, I knew about this problem of having data. In fact, I'd done it. Data from a flight. How do you estimate the states of the missile during the flight? And when I first saw his paper, I just jumped out of my chair. This is it. Take the measurement and compare it with what you thought it was going to be. That's an error. You multiply it and feed it back to change your model. And so I was really delighted to discover that. And I went on then to work with an engineer at Raytheon, and I showed that his filter was actually a part of a calculus of variations problem in which you took all the measurements and went over them in the forward direction, which is the filter, and then backward over the same measurements, so that even the initial one would be affected by the measurements at the end. So it's a 2-point boundary value problem of optimization, forward and back. And so that we wrote a paper on that, which I think was a pretty good one. It showed that the Kalman filter was a part of a program of fitting data by the least squares to over the whole path of the dynamic period. And unfortunately, I did that on an Air Force contract, which from Wright Field, which was published in a obscure report from Wright Field, so not many people saw it until later. And but it made me feel good because I thought I really understood the Kalman filter. Kalman's original paper was very mathematical, using Banach spaces and so forth. And I didn't really understand what he was doing. I knew the result must be right, but I didn't know how he got there. So I worked with this other fellow to try to figure it out my way. And I figured it out as a 2-point boundary value to optimize, which had been done long before by astronomers tracking stars. You have all of these data on where it is, position as a function of time, and they would make a least squares fit to that because they knew that their sighting angles were not quite right, and so they would estimate them by running them back and forth. So that was well known, and as least square fits, weighted least square fits. And I think this was new to Kalman. He didn't realize that it was a sub-branch of weighted least square fits, but I nominated him. I wrote a letter supporting his nomination for the Draper Prize, which is sort of the Nobel Prize of Engineering.
Right.
And he got it. And I think my letter helped a lot because I really admired what he had done. He had kind of a personality that's not very easy to get along with.
Is that right?
But he's a great guy, and he made a great contribution.
And were you able to see the application of the work that you were doing?
Oh,
with
yeah.
This?
Yeah, that is fun. People use some of my optimization theory and optimal control theory at Boeing and at Hughes and Lockheed. And so I saw the results from those. But it was really through my students who went out and propagated the ideas that a lot of them went to work for industry. In fact, only a few of them went into academic fields.
Oh, interesting.
Which, so, yeah, I saw a lot of applications. And of course, when I was at Harvard at Raytheon, they were using that stuff directly.
Right, in the Falcon missile or the Hawk missile. Yeah. And then I know you got into work in helicopters at some point as well.
Well,
is that sort of the same part of optimal control or something a little different?
Well, at Harvard, they gave me different courses to teach every year. And I love that because you really learn a subject when you teach it.
Mm-hmm.
And so I finally got to teach thermodynamics, and it's a very difficult subject. And that's the way I learned it there. And so I had the idea when I came here as department chairman that it'd be nice for people to take a new course once in a while, learn something new, learn what their colleagues are doing. Some people liked that, some people didn't.
I bet.
They wanted to teach their old course and continue to do it that way. But it's a kind of a philosophical idea. I think it's good for a department if people learn their colleagues' fields, teach a course. That's the way to do it.
Yeah. So in the maybe 80s and 90s, could you talk a little bit about what direction your research took sort of in the later part of your career?
You started asking me about helicopters.
Yeah.
Well, that was a course I had a engineer at the Army. It was an Army-based research in helicopters at NASA, NASA Ames. And there was a fellow there named Schmidt who I invited to teach a course in helicopters because he was involved with that every day. And he taught a wonderful course, and then he went back to Princeton and got a job teaching there. And so I had an opportunity then to teach it myself with his notes and several good books on the subject. And helicopters are complicated. The rotor dynamics and aerodynamics are extremely complicated because each blade of the rotor is hitting the wake of the blade ahead of it, and makes a very complicated thing to analyze. And so you simplify it by making disk theory. Just treat the whole flow through the disk, and treat the air all together being turned, and that gives you some simple ideas that work out pretty well. But to get the details, I had one of my first students here at Stanford, Earl Hall, had worked for a Bell helicopter also. And so he had more knowledge than I did about helicopters, and he did a thesis on helicopters, which I barely understood at the time, but I do now. And so that he wrote a paper which involved a pretty good approximate dynamics of the rotor, which had never been done before. So that was a pretty good paper from that.
Yeah.
And of course, all the Vietnam War protesters were breaking our windows in this building during the
in the Durand building,
protests. And one day we were listening to the campus radio, and the group had convened on White Plaza, and they decided they would come over to our building and talk with us about why we helped the military build helicopters, which we didn't, but they thought we did. So I said, well, I'll be brave and I'll get up there in the front steps of Durand and I'll meet them and I'll talk with them. Well, I get out there and they walk right past me and up and talk with the graduate students, which is a much better thing to have happened than my speaking to them. They were their own age and they were heavily involved in teaching and knew that we weren't directly involved in the Vietnam War. Nonetheless, we got all of our windows broken, the big plate glass windows. We had plywood in them for a long time. And my daughter was undergrad student, and she came over and tried to defend against the window breakers, but they outnumbered her.
Yeah, that was pretty brave.
Yeah.
Yeah.
Maybe stupid, silly.
Yeah, maybe.
Better description.
I mean,
I still think that the people who broke the windows were not students, but people who are worked up about the Vietnam War from the community. I'd like to think that anyway.
Yeah. Did they come in your class once?
Yes. How did you know that? Yeah, I had one class. I forget what the subject was, but they're in there before I arrived at the lecture hall, and I behaved badly. I look back on that and say, I wish I'd sat down and talked with them, but I was angry because they were interrupting my class. And so I went to my office and called the campus police. Of course, they dispersed before the police arrived, but I wish, looking back, I'd sat down and talked with them. Yeah.
Was it over the Franklin case, do you recall?
No, it wasn't the Franklin case. It was the Vietnam War, which Franklin case was involved with the Vietnam War. But
right.
Yeah, he was. I remember seeing him come from the computer center. He was leading a protest at the what then was the computer center on the north end of the campus, and well, it's still there. It was just a bunch of shacks, but he really. I heard him talk. He was really inciting them to do damage, to break windows and do things, and other people heard them too. And so I think he's one of the few tenured professors that ever got fired.
That's right.
At Stanford.
Right.
And rightly so.
Now, were you on the academic senate at that time?
I think I was.
When this was
around
happening?
that time. I was in the Senate. Yeah.
Yeah.
And yeah, it was a difficult time. Very difficult time. I was I was in the Senate, and they asked us to be present at a known protest that was coming up. I forget exactly where it was, but somewhere right on the campus. And because we're in the Senate, they thought, well, we'll give them green armbands, and they'll watch the police and make sure they don't use too much violence against the students, which is a good idea. But we assembled over at the sheriff's station on the campus and a bus. And as we drove over, we got almost to the place we wanted to go to when somebody threw a brick through the windshield and cut the driver's face pretty badly. And so we got out and walked from there. And here we were with our green armbands, and the San Jose riot police were there with shields and batons, and on come the students. And a very tense situation. I remember one girl who was shouting at the police and so forth, who just broke down in tears. Feelings were so high.
It was a tense time.
Anyway, we got back okay, but not a great experience.
Yeah.
To have to do that.
It must have been very frightening.
Yeah, it's crazy.
Yeah.
Yeah. But understandable because, you know, Vietnam was very controversial, and still is.
Yeah.
And
do you think those events changed you in any way?
What changed me?
The events that you went through, and especially the targeting of, you know, kind of your research.
Well, no, I knew that we were working on basic things, which were not directly related to weapons, but of course they were used for making airplanes and helicopters. But airplanes and helicopters have good civilian uses too. Medical helicopters, ambulances, and of course all the airlines, so that I was convinced that our research was, when properly used, was okay and good.
Right.
And you have to have a military too, and so I didn't feel bad about supporting the military research either, but I felt kind of bad about the Vietnam War because I didn't think that was the right thing to do at the time.
Yeah.
And one of the students in my class invited me to one of the dorms for a dinner one night, and then pursued to question me after dinner about just what you're talking about. And he was kind of amazed that I agreed with him about the Vietnam War. He thought I was a crazy military nut. So I think I convinced him I wasn't.
Did having children that were young adults at the time, and did that shape your feelings about that time?
Sure did. I had two boys who were subject to the draft, and two girls who were, one at Stanford and one at UC Davis, who were very much involved in all this protest activity. They weren't, none of the, well, no, I'll take that back. My older son was involved with what's called the SDS at Harvard.
Right.
I forget what the initial
Students for Democratic Society,
Students for Democratic Society. He was very much involved with that, and felt strongly about the thing. We didn't discuss that very much. He'd come home for Christmas and Thanksgiving vacation and summer, but we didn't talk about that very much. I kind of approved of his being in the SDS, just the way I think the students here were right to protest the Vietnam War.
I've often wanted to ask, after all of the upheaval in the early 70s, how did things kind of get back to normal?
That's a good question.
Or maybe they never got back to normal, but how did things
Well,
heal?
yeah, in the early 70s, as chairman, I was subject to a lot of pressures from all directions, but I told you I felt that the basic research we were doing was useful all over, and but it was hard because the students after the Vietnam War didn't want to go to the work for the military, and the military cut back on research funding. So we had a difficult time in the early 70s with funding. Not me personally, but the professors in the department. It was hard to get money at that time. And there was a point there where I think Dean Kayes was thinking about putting aeronautics and astronautics back into the mechanical engineering department. Came talking with me about it. I said, no, I think we would need to keep an aerospace department. The whole new field of space was developing then, and clearly there was going to be a lot of interesting research in that direction, and apparently I convinced him to let us continue. But that was a low point in the department's history in the early 70s there. It was not so clear that we were going to continue.
When you think about the department at Stanford versus the departments at Harvard and then Caltech, is there anything that really differentiates Stanford in your opinion?
Well, that you can ask me about MIT too. We have, I think, let me tell you what my opinion is about Harvard and Stanford students. The Stanford student is cool. He works hard, but he doesn't talk about it. The Harvard student worries and worries. He competes with everybody directly. Don't do that here. That's not cool. So it's sort of a different attitude that the students have. They're both groups very bright and very hardworking, study hard, but their approach is quite different. And I found that same thing. I taught 1 year at MIT. I was invited to be a guest professor there for 1 year, and got the same opinion of the students there. The faculty in the aero department at MIT treated me very nicely, and I had a lot of fun. I taught the first course in optimal control there that had, and in it I had 2 or 3 students who later became good friends, and so forth. So that was a great experience, teaching at MIT for 1 year.
Yeah.
And Caltech, I occasionally got a little annoyed with Caltech as an alumnus because they weren't treating engineering very well. Fortunately for them, my colleague Bob Cannon came back from a job in Washington. He was on leave from Stanford, and they hired him away to be the Dean of Engineering at Caltech. They don't call him that, they call him chairman.
I see.
But he found that the reason they didn't have any assistant professors. Why don't you have any assistant professors? Well, because the whole faculty, engineering faculty, votes on every promotion and hiring. Well, each department wanted to hire in their department, so they vote against the guy in the other. And Bob quickly said, "We're going to stop that. We're going to," and he hired, I think he said, 14 or 15 assistant professors in the few years he was there as chairman, and just rejuvenated the engineering school at Caltech. And he came here, and I invited him to come here because I was tired of being chairman, and I knew he was doing a good job there, and I knew he was getting a little unhappy because a new president had been appointed who was a physicist who thought we ought to get rid of engineering at Caltech. And so he was ripe for coming here. So I told Dean Kays, and Kays invited him, and he came and did a wonderful job as chairman. He's a very good research and faculty administrator. So Caltech's a very exciting place. So when I went there from Iowa State, I was blown away by the competition. Everybody there was as good or better a student than I was, and I'm used to being the best student in the group at Iowa State. It was quite a shock. I got my first B grade in a course, and so that lifted me up by my bootstraps to get going. And of course I arrived a month late because my first son was being born in Iowa, so I had to catch up. But that was simply a great experience. Liepman, my professor, and all the professors that I had there at Caltech were just first rate. I think the ranking group people at which magazine is it? Newsweek ranks them number 1 now.
Oh, right. Interesting.
Yeah. And it's a great experience because it's only about less than 1,000 students, and and they're all top notch, and all the professors are top notch, Nobel Prize winners. Oh. So that's the place to go if you want to do engineering or science. Stanford's not bad either.
I was going to say something nice about Stanford.
Stanford's not bad either.
Yeah.
But Stanford has the advantage that they have liberal arts. As an undergraduate, you can take courses in the liberal arts as well as engineering. which I did at Haverford, and I thought I benefited from that very much.
So I want to ask you about your retirement. You retired in, I guess, 1993. And what sort of led you to decide to retire at that time?
Well, I was thinking that we needed some new assistant professors, and if I retired, we'd get an assistant. I was right on the boundary between the people who had to retire and those who didn't. I was just over the line, so I didn't have to retire, and at age 65. So I stayed on 3 years and retired at 68. But I said, I'm getting bad reports on my teaching because I've taught those courses so long. I think they're easy, and the students don't think they're easy, and so I'm not catching the vibes that they send to me on their difficulties. So I said, well, I ought to get out of here and make way for a young assistant professor to take over, and so I did.
And then what did you do after that?
Well, I wrote 3 books.
Oh, so you weren't retired so
things
much.
that I had taught, and that kept me busy. And I taught a few courses for a while after I retired, but then began to get really bad notices on my teaching, so I said, that's it. I'll stop that. And so...
And did you and Helen get to pursue some things that you had been putting off, maybe?
Yes. Then we began to travel, and we traveled all over the world. South Africa being one, where I had these 2 graduate students. That was a marvelous experience. To Germany, where I had this wonderful German student at Munich, near Munich. I had a Russian postdoc from Moscow Aviation Institute, Yuri Plotnikov, who invited me to come there, and I went there for a international meeting, which my dad gave me a little extra money. He said, do something you wouldn't have done if you didn't get that money. So Helen and I went out to Central Asia, to Samarkand, and that was just wonderful. It's I understand. Well, my wife was very interested in history, so she, of course, read up on all these places we were going, and she's so curious. You want to learn more.
Yeah.
So she's a great one to travel with.
I bet. Now, you told me she went and pursued additional education after the kids
She got her
were grown
bachelor's
up?
degree at Notre Dame de Namur,
Yes.
which is up here in San Mateo or Belmont.
Belmont, right.
And got a degree in history, which was her first love, and also in home economics. And then she got a job teaching home economics in Redwood City, where her classes were mostly Latina. And that was an eye-opener for both of us. The Latina culture was quite different than what we had expected, but it worked out. And then she came and taught, I think, for 1 year at Palo Alto High School. And after that, she decided, well, I'd like traveling. Let's travel.
Yeah. And was she involved with the Faculty Wives Club, or was there some kind of a women's group that she was involved with at Stanford?
You bet. She got involved with Bill Fairbank's wife, who was starting a program called Second Careers for Women. And she worked with her on that and had several conferences, put out a book or 2 on how to start a second career after your kids are up and out of the nest. And so she did a wonderful job there.
Interesting. I wanted to ask you just a couple more questions before we conclude. You've been really received quite a few honors. National Academy of Engineering, the National Academy of Sciences, and in 2010 the Daniel Guggenheim Medal, and that's just a few of them. I wonder if among all those awards, was there any one of them that was particularly meaningful to you? Or? talk about a bit?
Guggenheim Award was a complete surprise. Came out of the blue. And the first one to get that was Lindbergh for his flight over the Atlantic. So that was quite an honor. And of course, the list of people who had gotten that Guggenheim was just the honor list of people in our field. So I was very honored to get that one. But our professional society, the American Institute of Aeronautics and Astronautics, also gave me a award of being, what do they call it? It's their top award in the field. I forget what they call it now, but that was quite an honor too. And yeah, there are quite a few other more minor honors that I got, which were nice.
Yeah, and when you received those awards, they describe your contribution as being primarily in this area of optimal control. Would you say?
Yeah, I think that was what people regard as my biggest contribution. My work on transonic flow sort of never got published, but I think as far as a scientific understanding of transonic flow, that was one of my major contributions. Not the engineering, that was already done, but
And figuring out what was really going on with that.
What was really going on.
Right. Okay. I'm going to just pause for a minute because we're getting ready to conclude. I'm going to look at my notes, and I want you to think, is there anything else you want me to ask you about before we conclude? I normally ask about, let's see, I didn't ask you about your diary that you keep.
Oh, okay.
Maybe we'll throw in a question about that. And you mentioned, sometimes I ask about recent directions in the field. Do you want to talk about anything like that with the drones or anything?
Well, I
offer a few comments.
A few ideas.
Okay.
We already started maybe 20 years ago to get interested in biomedical problems.
Okay.
Flow of blood in the human being is a fluid mechanics problem, a very complex one, because blood is such a complicated mixture of cells and fluids.
Okay.
And
hold that thought for a minute, and then I'll ask you.
And then, of course, bones, the deflection of bones, and so forth. Professor Chuck Steele got involved in that, worked with some people in the medical school on that. So that was the beginnings of BioX in the engineering school. We were one of the mechanical engineering had the design division. They also were moving in that direction. I worked with one student there who was working on simulating a robot walking.
Oh, okay.
Which is interesting.
I think I might have seen that. Hold on, let me ask you, and then we'll cut out this little part. I'm going to ask you about recent research interests or new directions in the field, and then maybe we'll close with a favorite Stanford moment. And I'll throw in something about the diary there. Okay, anything else you want to talk about?
My favorite Stanford moment is all the years I've been here.
Okay, that's a long one.
They have treated me so well.
Okay, well, hold it. Save it.
I enjoyed it.
Okay. I wonder if you could talk a little bit about recent directions in the field in the past maybe few decades, or either directions in the field or what your current research interests are.
Yeah, I think as far as the department's concerned, definitely a shift toward biomechanics and both in the structures, human structures, bones, and heart pumping and all, artificial hearts and so forth. Of course, your friend
Makovsky,
very much involved in that too, in electrical engineering. But we had a young woman assistant professor who worked in that field with somebody in the medical school, and I think if I remember her name, I can't. But she left us and went back to Berkeley to marry her supervisor, which I had a double attraction to go back. So she was great. Claire was her name, and I'll think of her last name in a moment. But she started to work in that field, and many others got interested in biomechanical problems. Chuck Steele being another one I've mentioned, that being deflections of bones under stress. And and then way back when I first joined the department, there was a Swiss-American professor whose name I can't call up, but anyway, he left here and went back to ETH in Zurich and founded a biomechanics department there. And I visited him there later one year when I was asked to do some consulting at ETH, and he had a big going program. So he achieved some suggestions and ideas from here. And I think that's a direction that's the whole engineering school is getting involved in it. And it's so exciting because the human being is such a complicated device,
right.
machine, if you like. The brain being the ultimate complication, much more so than just a computer.
Right.
And we still don't quite understand all the things that the brain can do. And so I'm sure bioengineering is going to continue to be a very important field.
Mm. And in the field of flight controls, have you seen any interesting developments there?
Flight controls, of course, have become pretty much standard. Autopilots are in use all the time. They make better automatic landings than pilots can make because they have more rapid response, and they have accurate sensors of altitude and attitude. So they can respond in a microsecond to what's going on. The pilot takes him a millisecond or longer to respond. So I had a story on that. Got time for a story? I had a student whose father was a 747 pilot and was teaching other pilots to transition from other aircraft to 747s. And he said his father had one student who came in and made 6 sloppy landings, bounced all over the field. And then on the 7th one, around came it perfectly smooth, made a gorgeous landing. He said, "Oh, great, you've learned how." He says, "The heck I have. I put it on autopilot and I watched it." So that sort of tells you something.
Yeah.
Yeah.
And with the drones, I imagine the drone technology is...
The drone technology was really... Some of it started right here with Elon Crow, who's... he had students building... we didn't call them drones then. They were just model airplanes with cameras in them. And he had them fly. He built them right here in the Duran building and flew them. And so in a way, the first drones were built right here. And I remember one of his PhD students had a stabilized camera, I think, which, if the airplane's bouncing around, you don't want the pictures to do that. So you put it on a platform which is held steady by a gyro, and the camera's mounted on that. That's standard now. And so I think we've had a great influence on the drone business too.
Interesting.
The big drones, of course, again, are just autopilots, and they're controlled by some guy in Texas who's in touch with a satellite that's in touch with the drone, which has a television camera, and he's watching the television camera fly into onto a tank or a truck or something.
Right.
And
Amazing.
there's a lot of interesting
Right.
moral questions on that too, but
Yes.
it's certainly a lot safer for the pilot.
That's right. So, you mentioned to me at one time that you keep a diary and have done so. I wondered if you could just tell me about that quickly.
I call it an annotated diary. When I was a professor, I got used to carrying a little pocket notebook to keep track of appointments with students, and got to putting events of the day in there to remember them. And when computers came along, I said, well, I'll take those and I'll transcribe them into a diary. And then, of course, digital pictures came along, and so it's very easy to put a digital picture in this typewritten diary. So I call it an annotated diary, which is illustrated, has pictures in it. So it's fun for me to look back and remember these events, and it's fun for my kids to read that because they can find when did we do that, you know, and what year was that we did this, and so it jogs their memory on trips that we had.
Right. And when you look back at thinking about all those dates and all those entries and so many of them here at Stanford, is there a special moment or something that really stands out?
No, special moments were almost every day here at Stanford.
Thank you for your service to the university. And thanks for joining the Stanford Historical Society today and recounting this oral history.
Okay, thank you.